All right, how's everyone feel today?
Totally awesome, sir.
All right, that's what I like to hear. So today I want to answer this question here. How can the magnetic force that's exerted on a moving charge be used to actually produce the electricity in the wire? In other words, how can we use magnetism to generate electricity? So before we answer this question, let's just quickly go back and review the magnetic force on a current carrying wire. If I have this set up here and I close the switch, if I close this switch right here, as soon as I close that switch, since this is the positive and this is the negative, I'll get a current going this way. And then the current in the wire, it looks a little bit like diagonally and up, but it's actually supposed to be into the page. I'm trying to draw a three-dimensional picture on a two-dimensional plane. So this current right here is actually, into the page. And the current comes around this way and all the way around, and the light goes off. But that current inside the magnetic field is going to experience a force. And you could use the third right-hand rule to determine the direction of the force. If you put your fingers with the field lines, and you put your thumb in the direction of the current, your palm tells you the direction of the force. So I put my fingers with the magnetic field lines due to the bar magnets. I twist my hands so that my fingers are still with the magnetic field lines. My thumb is going into the page, and then my palm faces down. So there'll be a magnetic force acting on that wire. And this force could be harnessed and used to turn electric motors, or this force could be used to deflect electric meters. But we could also modify this third right-hand rule, and instead of saying that the thumb points in the direction of the current, another way of thinking about it is the thumb points in the direction that the positive charges are moving. So here's a positive charge in the wire, and it's moving this way with a velocity. And here's another positive charge, it's moving this way. And the positive charge is moving this way, and the positive charge is moving this way, and the positive charge is moving this way. So the thumb could also be placed in the direction that the charges are moving. So fingers go with the magnetic field lines, thumb goes with the way the charges are moving, and then the palm shows the force, which would be down. So that wire would be pushed down. So we're going to make use of this modified third right-hand rule, and we're going to see how we could actually generate electricity using that magnetic force. So here I have a similar setup, but notice there's no battery down here. Down here, there's no battery at all. It's just a wire with a light bulb, and the wire goes in between the two bar magnets. All the wire is the same thickness. I just kind of magnified it in the area between the bar magnets. But at first, there's no battery, so there's no current. No current, that means the charges aren't moving, and if the charges aren't moving, they're not experiencing a magnetic force. It reminds me of the line, is something supposed to happen? So human ingenuity and engineering feat here, it was discovered that if a person came in and physically moved the wire, the charges in the wire would go for a ride. So imagine a person right here, Again, this is not going to be drawn to scale, but here's a person, and they're going to grab hold of this wire here with their hands, grab hold of this wire, that's their hands, and they're going to physically move the wire downward. And when that wire is physically moved downward, the charges inside the wire are taken along for the ride. So this little charge right here is going to be moving this way because it's inside a wire that's being moved downward. This little charge here is going to be moving this way because it's inside the wire that's being moved downward. This charge is going to be moved this way. This charge is going to be moved this way. These charges are going to be moved downward. Now, recall from before, we established that charges that are moving in a magnetic field, whoopsie, experience a magnetic force. Now the charges aren't moving because the battery is making them move. Now the charges are moving because they're inside a wire, and the wire is being physically moved downward by some person, and the charges are going for a ride. So we're going to apply the third right-hand rule, modified style, to determine the direction of the force on these moving charges. So once again, your fingers go with the magnetic field lines of the bar magnet. And then your thumb, it's not going to go in the direction of the current because remember, there is no current in the first place. It's going to go in the direction that the charges are being physically moved. And then the palm ends up showing you the direction that each one of those little charged particles is going to experience a force. So put your fingers with the bar magnet's magnetic field lines, keeping your fingers going to the right, your right hand's flat and open. Turn your hand so that your thumb points down because that's the way the charges are being moved, because they're being taken for a ride, because the whole wire is being moved downward. If all of the charges are physically being moved downward and their velocity is downward, well, they're going to experience a magnetic force. And what's going to be the direction of that magnetic force? Out of the page. So they experience a magnetic force out of the page, down the axle of the wire, out of the page. Now the interesting thing is, once we establish that all those charges inside the wire are going to experience a force out of the page, that magnetic force is going to push all those charges in that direction. So they all start to flow in that direction, and you get a new induced current flowing that way. And it's not just going to flow there, it's going to push the current here. It's going to light up the light bulb, and the current's going to be going here, and the current's going to be going here, all because inside here, when the charges were physically moved downward, they experienced a force out of the page down the axis of the wire. This whole process of producing electricity by physically moving a wire is known as electromagnetic induction. And this force right here sometimes is referred to as the electromotive force. And the acronym for electromotive force is EMF, because what you're doing is you're using this right here to generate a current. So this is kind of like acting like your battery, but it's not a chemical reaction. It's using a magnetic force to generate the current. So this here is the EMF. And you're going to be asked to find the direction of the induced current, and you can do it by figuring out what's the direction of the force on those charged particles. Or there is a fourth right-hand rule for determining the direction of the induced current. So far we figured out the direction of this induced current by using the third right-hand rule. But the third right-hand tells you the direction of the force. But then if you know they're all going to be forced out of the page, well, then the new current is going to be out of the page. So you make that leap of understanding that the new current is in the direction of the force, because the third right-hand rule gives you the direction of the force. But sometimes people find that confusing, because in the past, the thumb used to go in the direction of the current. And now the new current is in the direction of the palm. So it can be done using the third right-hand rule, but there is a fourth right-hand rule that allows you to figure out the direction of the new current. If you take your right hand, you have your thumb, your pointer finger, your middle finger, your ring finger, and your pinky. So this right here is your thumb. And this right here, I should have made this a little deeper here. This right here is your pointer finger. And this right here is your middle finger. You're going to fold these two fingers. You're going to fold these two fingers, your ring finger and your pinky finger. You're going to fold them down because you're not going to be making use of them.
Can I draw the diagram, because I believe I can make it really easy to interpret.
Okay, thank you.
I got you. All right, that's good.
That is amazing. Thank you, Johnny. Thank you so much. So you position your thumb and your pointer finger and your middle finger. So they're at right angles with each other. All three of them are at right angles with each other, like an XYZ axis. And what the fourth right-hand rule says is that you put your pointer finger in the direction of the bar magnet's magnetic field lines. And then you put your thumb in the direction that the wire is being physically moved. And then your middle finger tells you the direction of the new induced current. So you hold your thumb, pointer, and middle finger at right angles to each other, like an XYZ axis. Put your pointer finger in the direction of the magnetic field lines. Put your thumb in the direction of the way the wire is being physically moved. And then put your middle finger in the direction of the current. So if we did that up here, your pointer finger should be going in this direction. Keeping your pointer finger going in that direction, turn your hand so that your thumb points downward. Your thumb is going to point downward this way. Then your middle finger should point in the direction of the new induced current, which would be out of the page. So here's another practice problem. If you have a magnetic field that's into the page, so I'm not showing you the bar magnets, I'm just showing you the magnetic field lines. And then you have a wire that's going up and down like this, and then this wire is physically moved to the right. If you use the fourth right-hand rule, or like I said earlier, you can use the third right-hand rule to get the direction of the force on the charged particles and then make that leap of understanding that the new current is going to go in the direction as the force on the new particles. Or you could use the fourth right-hand rule, determine the current direction. So pointer goes with the field lines. Thumb goes with the way the wire is physically pointing, with the wire is physically moved. And then your middle finger tells you the direction of the new induced current. And what direction is that going to be, Ken? Upwards. So the new current is going to go upwards. So this is your answer. So of course, seeing is believing. Here I have a galvanometer. It measures just little tiny baby, currents. And I just hooked a wire to it. Notice there's no battery here. There's nothing going on here. So you're not going to expect the galvanometer to move, yes? And I'm just going to put this wire through this double horseshoe magnet. Now watch what happens when I physically move this wire and I move it through this magnetic field. The field lines are going this way. I just move the wire through the magnetic field and I'm generating a current. And notice when I move the wire one way, the current goes one way, and when I move the wire the other way, it goes the other way. So I'm generating current here that keeps alternating the direction. And what is this current called?
Alternating current.
Alternating current. There you have it. Producing electricity using the magnetic force that acts on charges when they're moving in a magnetic field. So cool.